Hello everyone. It's my pleasure to present to you about our work on the topic of kernel Blotto game with favoritism. So in this paper, we focus on the model of kernel Blotto game. It is a game. It's a one-shot complete information game between two players called A and B. Each player has a budget of resources called SA and SB. And in the game, there are n locations called n battlefields. Each battlefield will have a corresponding value. When the game begins, the players simultaneously distribute their resources towards the battlefields, and the outcome of each battlefield will depend on the allocation of the players there. For example, if the allocation of player A is larger than that of player B, then player A will win this battlefield and gain the corresponding value. Reversely, if player B has a larger allocation, he will win the battlefield and gain the values, and so on. So the payoff of each player will be the summation of the gains that the player have in all the battlefields. And a pure strategy set of each player is the rescale simplest like this. So this game it has a long history. And actually, it was first introduced exactly 100 years ago, and with the original application in military logistics. That's why we have the name kernel Blotto, and we have the terminologies like battlefield and so on. After that, it was applied to a large range of other application. For example, in political competition, the players are the political parties, and the battlefields are either the state or the voters. Another example that is mentioned in the literature is in to model the R&D contest, where the players are the companies and the battlefields are the technologies or the product that the companies are competing to produce. Another example is in airport securities, where the battlefields are the security targets and the players are the defenders and the attackers. So the basic scenarios of this application can be well captured by this very simple model. However, as we know, in practice, situations tend to be more complicated than the theoretical model. Especially, we want to focus on the cases where some players might have the advantages in some of the battlefields. We call this advantage the favoritism. And there are two types of favoritism that we consider in this game. The first one is called the pre-allocation. That is the resources committed and that is available prior to the game. For example, in the military logistics application, it's often the case that before the battle, the one side or maybe both sides already committed, already deployed their military forces or weapon into some of the battlefields. So that's what we call pre-allocation. In political competition application, the pre-allocation can be interpreted as the a priori position of the state or the voter. For example, California is a pre-democrat state, so the Democratic Party is as if this Democratic Party has a pre-allocation in this state. In the R&D context, the pre-allocation can be understood as the currently available technology or machine that will help the company to gain advantage in developing new products. Another type of favoritism that we consider is called asymmetric effectiveness. So in the classical formulation of the game, each unit of resources of player A has the same strength as each unit of resources of player B, and this happens across all the battlefields. However, in practice, this might not be the case. For example, in the airport security case, it only needs one terrorist to destroy a target, while it needs, say, 3 security agents to successfully survey an area. So it's as if one terrorist has the strength of 3 security agents. In R&D context, this also appears well because different companies have different machine, different technology, different team research that has different strength and different weaknesses in different areas. So motivated by this situation, in this work, we introduced a new extension of the game called kernel Blotto game with favoritism. It had the same setup as in the classical kernel Blotto. However, this time each battlefield will be assigned with two extra parameters called PI and QI. I will explain about this parameter later. So the outcome in each battlefield now will be determined by a new rule. So instead of only compare between the allocation of player A and the allocation of player B, we will compare the allocation of player A as A here with a linear transformation of that of player B with the parameter PI and QI. So if SAI greater than this quantity, player A will win the battlefield and gain the value, player B will gain 0. Otherwise, it's player B who wins. So in this model, PI represents the difference between the pre-allocation of the players. So if PI is a positive number, that means we subtract a positive quantity from the allocation of player B. It's player A who has the advantage. Reversely, if PI is smaller than 0, then it's player B who has this advantage. On the other hand, each unit of player B will be equal QI units of player A. So if QI is smaller than 1, then it's player A who has the advantage, and if QI greater than 1, player B has this advantage. And naturally, if PI equals 0 and QI equals 1, then this model coincides with the classical kernel Blotto game. And the key questions that we aim for in this work is to characterize the mass equilibrium of this game. So first, let me do a quick literature review. Characterizing the equilibrium of the Blotto game is notoriously challenging. The main difficulty is that the mid trajectory in this game is an n-varied distribution, such that any pure trajectory drawn from this mid trajectory has to satisfy the budget constraint. The budget constraint means that the summation of your allocation cannot exceed your budget. It is this budget constraint that creates a link up between the allocation in different battlefields. So if you want to do optimally in one battlefield, you might end up having no more resources to allocate to other battlefields. So it's a trade-off between allocation. The standard approach for finding the equilibrium of the kernel Blotto game is as follows. First, we focus on each battlefield independently and try to see what can you do optimally in each battlefield. In other words, you have to look for the so-called optimal univariate distribution. The optimal univariate distribution is defined as the distribution such that when players allocate accordingly, then the budget constraint will hold in expectation. And in each battlefield, see the best response against each other. Having this optimal univariate, if we can construct a feasible choice distribution, that is the choice distribution of this univariate distribution, such that this budget hold, the budget constraint hold, then we have found an equilibrium. However, even in the classical kernel Blotto game case, the construction of such choice distribution are currently only available in very restrictive cases. For example, where both players have the same budget, all the battlefield have the same values, or it only work where the number of battlefield is equal to 2. So in the cases that such choice distribution is not available, then in the literature, there are the work that use the optimal univariate to find the equilibrium of some relaxed game, to construct an approximate equilibrium. I will come back to this point later. Finally, to construct the optimal univariate, we need to study a related model called open auction. So in this work, we will apply this kind of similar approach to what we have here to our game with favoritism. I will leave the roadmap on the top for us to keep track of what's going on. So first, let's define the open auction with favoritism. It is the game between two players, again A and B, and they will compete for one common item. Each player will assess the item with a value, say UA and UB. When the game begins, simultaneously, both players will make a bid, say SA and SB. In the classical open auction, we will compare SA and SB, and the player who has the higher allocation will win the item. However, because we work with favoritism, so again, we will compare SA and a linear transformation of SB. And after the game, no matter which player wins the item, both players have to pay their bids. That's why we have the name open auction. This is the difference between open auction and kernel Blotto. So the state of the art of open auction with favoritism is that equilibrium result only available in the case where both players have the same assessment on the values of the items, and only one player has both of the favoritism. So our first contribution is to completely characterize the equilibrium of this open auction with favoritism in all cases. Well, it depends on the parameter configuration of the game that we have different equilibrium, but they have the form similar like this. That is, each player will bid 0 with a positive probability, and then uniformly at random in a range. This is the plot of the CDF of the equilibrium of the players in the case that this constraint hold. So we have found the equilibrium of the open auction, but this is not our main intention. We only use it to construct the so-called optimal univariate of the kernel Blotto game. And to do so, we consider n special instances of the open auction with favoritism. Each instance of the open auction depends on the parameter of each battlefield, and also depends on two auxiliary parameters called kappa A and kappa B. In each of the open auction, it will induce an equilibrium that we denote by FA kappa and FB kappa with the subscript index coincide with the index of the battlefield. Our main theorem is like this. It says that we claim that there exists a pair of parameters kappa A, kappa B, such that when players allocate according to FA kappa and FB kappa, in expectation, their allocation have the summation equal exactly the budget SA and SB here. The second result is that for every solution of this system, the FA kappa and FB kappa constitute a set of optimal univariate distribution of the game. So we have found the optimal univariate. What can we do? The direct corollary gonna be if there exists a feasible choice distribution, then we have found an equilibrium. However, as similar to the case of classical kernel Blotto, such choice distribution is not found, is not known in general. However, in some special cases, we can deduce some interesting results. For example, in the case of symmetric battlefields, let's see, all battlefields have the same parameters. Then apply the work from Robertson 2006, we can find an equilibrium. In the case that this is not applied, then we can use the approximation scheme of Wu and An in 2020 and show that by independently drawing from the optimal univariate, then rescaling to make sure that the budget constraint hold, we have found an approximate equilibrium of the game where the approximation error epsilon decrease when n, the number of battlefield increase. Finally, in some application, it makes sense to consider a relaxed game where the budget constraint only required to hold in expectation. We call it the general Lotto game. And in this game, by independently drawing from the optimal univariate, we found an equilibrium. So in the previous slide, I presented as if we just pick what known for the classical case and apply to the kernel Blotto with favoritism, and we have such result. However, it's not really the case. Actually, not all the technique, the standard technique are applicable in our case. For example, let me recall the main theorem that we presented in the previous slide. Actually, to prove the existence of the solution of this system is non-trivial. The reason is that this system is actually a two equation with two variable system, and these functions are quite complicated. If you see in my paper, in the classical case, this system will collapse. There are some trick to make this system collapse to one equation with one variables, and we can use intermediate value theorem to prove the existence of the solution. However, this trick will not work in our case because the presence of the parameters represent the favoritism. The second problem is that if you, the second problem is that for constructing the optimal univariate, we need to solve this system, and naively solving this system will be inefficient because you see that for every configuration of the parameter, this fa kappa and fb kappa will change, and the whole system will change. So to solve it means that we have to consider all the cases of all the configuration of the parameters. So it will take us exponential numbers of time in terms of the number of battlefields. So to solve this, we use a topological approach, and we prove the existence by the theory on winding number. And we propose an algorithm that can find a delta approximation solution of this system, where delta is a arbitrarily small parameter, and it only takes linear time to do so, so it's efficient. So finally, to justify the effect of the favoritism on the payoff of the players, we conducted some numerical experiment. So in this experiment, we consider a game with 4 battlefields. The 4 battlefields will have the same parameters, symmetric. So each battlefield will have the value of 1. So the maximum payoff that a player can get is 4, and minimum is 0. So in this plot, the x-axis represents PI, which is the pre-allocation in each battlefield. The y-axis is the payoff of the player A, and each curve corresponding to a parameter Q, which is the symmetric effectiveness. So we observe that when P increase and when Q increase, that is the favoritism inclined towards player A, his payoff actually increase. So which is confirm our intuition. We see some discontinuity in this plot because when one player has very strong favoritism, there is a trivial equilibrium. That's why they jump here, where player A will guarantee to win all the battlefield and guarantee the payoff of 4. And here it means he